I have your exam grade. I'll give it back to you. I did the hour. You have one more homework assignment. You should be able to do the first two problems now. After the lectures, we'll be having fractions. Hopefully I can start talking about response service methodology today. Any questions? I gave you reading assignments, I think, last time, for most everything we'll talk about. If not, I'll give you sections from the text that you can read if you want more information. Okay, so what is a fraction? It's just part of a factorial, and one way to get them is just using confounded factorials, right? So if you're going to use a confounded factorial to get a fraction, tell me how you do it. Just the basic idea.
Confound something, then take one of the...
Confound something, or several something.
Yeah.
And then choose one of the blocks. That's it. Just a single block from a confound factorial. And so, well, they're good, and it can give you some information on quite a few facts, but they're bad in terms of you have aliasing, right? What is aliasing? Ying, right? What's aliasing? Anybody?
So when you, like, the result from something could be the same as
another.
another.
It's just special name for confounding. It's like if I have A aliased with effect D, they're two main effects. So you can't separate those two. So you need to understand how things are confounded. You need to understand aliasing if you're going to use these. That's the one of the major problems. What's the other major problem with factorial? Fractional factorials. You have this complex aliasing, right? Because you get confounding on these things. So you can't separate the effects of the factors necessarily, depending which factor you're looking at may be important. But there's a difference. You also lose information, totally lose information on some effects. Which are those?
The higher order.
Well, the ones that you use to confound. When you confound an effect with incomplete blocks in a confound factorial, you usually can get information on the effect that you confound because you replicate these things, right? But with a fraction, you confound it and you totally lose information on that one effect because you only take one block. So you lose total information on those effects that are confounded. You get aliasing, okay, which means that you can't separate the effects. But you do save a lot of money and it allows you to look at a lot of different factors at once. Okay. So that should be in your bag of tricks, in terms of experimentation of your research. Okay, so I'm going to eventually move into where we're getting to smaller and smaller fractions. And to do that, along the way, there's a special way how we can identify treatment combinations for fractions without using the X matrix. Okay, kind of similar to the idea that we used to identify blocks before. So identifying treatment combinations for 1 over 2 to the m, 2 to the n fractions. Okay, it's difficult to use the X matrix. Okay, that's one thing. We could use ideas from confounded factorials. What do we do there? We use mod equations, right? I think in the general way, use mod equations. There it is, mod equations. Well, both of those are kind of difficult. Especially this one, get the X matrix. That's kind of a pain. You have to code it, right? Didn't see it. The mod equations are a little bit easier. You can write a little loop to generate it. But there's an even easier way, okay, to get fractions. And so what we're going to do is we're going to we can use the columns from a full 2 to the n minus m factorial. Use the columns from a full 2 to the n minus m. You have to get that number, and so if that number is 3, it'll be a full 2 cubed factorial. To get a 1 over 2 to the m, 2 to the n fraction. Okay, so we got at least 3 ways we can get it. This is an easy way. And it's really quite easy to see. So I'll give you an example. So I'm going to have a 2 cubed. Let's see, I want a 1 over 2 to the 1. M is 1 in this case. 1 over 2 to the 1, 2 cubed. So I want a half fraction of a 2 cubed. Right? This actually that's the simplest example I gave for the confounded factorials. Right? We start with a 2 cubed, we have blocks of size 4, right? So that's kind of what that is. It's the same kind of idea. We're just going to take one of the blocks. Okay, so we want this fraction. So what is it? I want a 2 to the n, so this is n here, and this is n, maybe I should say, parentheses, that's n, and this is m, right? Okay, so the 2 to the n minus m is 2 to the 3 minus 1, right? 2 to the 3 minus 1 is equal to 2 squared. So I want a 2 squared full factorial. That's what I'm saying here. That n minus m is coming from this thing. N minus m here. Okay, so I want a 2 squared full factorial. Well, let's get that. That's really easy. Let's just take factor a and b. And I'll say, let's say plus, minus. Well, I can put 0, 0, 1, 1. Doesn't make any difference, right? Okay, plus, minus, plus, minus. Right? That's a full 2 squared factorial. Okay. Now, what do? I obtain a new column. So I can multiply those and get the interaction, right? So if I get the interaction column, what do I get? Plus 1 by plus 1 is plus 1. Plus 1 by minus 1 is minus 1. Minus 1 by plus 1 is a minus 1. Minus 1 by minus 1 is a plus 1. Right? Turns out that is a fraction. In fact, it's exactly the same block that I gave you in the first block when we started talking about confounded factorials. Remember that? If I would get the other one, all I did is get the complement of this. Do you remember? If I got the other one over here, it would be minus, plus, minus, for the AB. Well, how do I turn this into a fraction? I just say, oh, we're going to let factor C equal AB. That's it. So I just take a lower order full factorial and just multiply the columns, get the interaction columns, and then just relabel those. Easy, really easy to get. In fact, this is the way SAS does it. So this is a half fraction of a 2 cubed, right? Did we see how to do this? What's defining contrast? Well, no, this is not really C. We're saying this. We're saying C is aliased with AB. All right? So we've defined an alias. So by doing this, I'm taking this column is just a product of those two. I'm basically defining C to be aliased with AB. Now, if C is aliased with AB, that's not the defining contrast. Now, how can I get it? I can just multiply C on both sides. Okay, so if I just take C and multiply on both sides, I get C squared is equal to A, B, and C, right? Okay, well, C squared, but that was just going to be 1. I'm sorry, A, B, and C. If I multiply C on both sides, and this turns out to be defining contrast. So I just take this, and what this turns into really is the 1. is I just take each effect and then just multiply through to turn that to 1, basically, or it'd be c squared, and in mod 2, c to the 0 is 1, right? Any number raised to the 0 is 1. So this is 1 is equal to ABC. That's like the column in your X matrix. It's exactly the same. It's 1 throughout your whole X matrix. Defining contrast is ABC. That's exactly what we did with the confounded factorial when we decided we're going to confound the ABC interaction, right, to identify the blocks. Okay. So it's an easy way to get these. Okay. So let's do a bigger one then, a little bit. How about, so this is equal to 1. Let me give myself a little more room here. So I can say c squared. That c times c is equal to ABC. But c times c is c squared, which is equal to 1. So 1 is equal to ABC, so that's defining contrast. Let's do another example. I've got, let's see, a 1 over 2 squared of 2 to the 5th. I want a quarter fraction of 2 to the 5th. How many trig combinations do I have here in total? 32, right? Okay, and so I want 1/4 of the 32. So how many u's am I going to have in my fraction? 8. Okay, so I just want one block of 8. Okay, so really it's like I have to confound 2 effects, right? There's my m. I got to confound 2 effects. And so what does this mean? Then I get, so here's another example. And then I'm going to get the 2 to the 5 minus 2, which is 2 cubed, full factorial. Okay, let's get that full factorial. Well, that's an easy one. So it's a 2 cubed full factorial. It's the same thing, except I got more pluses and minuses. All right, and then plus, minus, plus, minus, minus. By the end of this class, you ought to have this down. Plus, minus, right? Okay, there's my full factorial. Okay. How many more factors do I need? I got 3 factors right here. Here they are. Okay, if I'm going to get a design, I need 2 more, right? Because why? I want 5 full factors, so I need 2 more columns out here. Okay, which of the easiest ones to do? We'll just take AB. The AB column is going to be what? Plus, minus, plus, right? And then, I don't know, BC, right? BC is going to be plus, minus, plus, minus, plus. Okay, now how do I turn that into a fraction? Robbie. Before Robbie's just sitting in class. How do I turn this into a fraction? I need 5 factors, right? I got 3 here. Where are my other 2 factors? Let's call this one D, right? D is equal to AB. And then let's call E is equal to BC, right? Okay, why am I defining contrast? How many defining contrasts do I need? M is 2, right? What are the 2? So defining contrast, I got 2 of them. M equals 2 on what? A, B, D, using that rule over here. And then B, C, E. Right? Now, I have M is equal to 2. How many additional effects am I going to get because of generalized interaction? 1. Right? It's 2 to the m minus n minus 1, so 2 to the n is 4, minus 2 minus 1 is 1 more. I just multiply it, and I can get the generalized interaction. Now I can get all aliases, because I have all 3 defining contrasts, and I can just take each term and multiply it times all defining contrasts and get all aliasing. Right? Okay, so maybe I should write out some of those. In fact, let's get the ANOVA and see what you actually estimate. So to use these, you have to know a little bit about your experimental material. You ought to be able to make a good guess. Now, I've said this before, I think, I'm not sure in this class, but what distinguishes good scientists is one that have good judges. And they can kind of see around the corner a little bit. It certainly fits in here, because if you look at, say, you look at the ANOVA, let's say A. What's A going to be A-list with? A is going to be A-list with what? BD, right? BD plus what? ACE, BCE. And what's the generalized interaction here? It's going to be A, C, D, E. So then this is going to be A-list also with A, well, it'd be C, D, E, right? So if I do an ANOVA, how many total degrees of freedom am I going to have? I'm going to have 7, right? When I do an ANOVA, I can have 7 degrees of freedom. I have 1 degree of freedom for this effect. I think I'm estimating just A, but not only estimating A, I'm estimating B, D, A, B, C, E, and C, D, E. Right? Okay, so now I'm going to have all the main effects. There's going to be 5 of them down here. The last one is what? E. And E is A-list with A, B, D, E. You can check this. Make sure I didn't make a mistake. DC plus DC. And of course, maybe I shouldn't be careful. I'd be careful about putting the pluses and minuses in here. Maybe I should just put commas to demonstrate that you got to be careful on the pluses and minuses. Just do this and make it easy. Okay, because you just want to see what's A is. Okay, so E is then A, B, D, and then BC, and then ACD. Is that right? ACDE, that's right. BC, okay. ACD. Well, what would you say about that effect? Both of them are A-list with what? First order two-way interactions. That's not the greatest. Okay, so if I look at all these, I'll have 5 effects for the mains, right? Here are the mains. How many more left do I have? I got the two-way. Let's just put two-way in there. Okay. You can tell the two-way, which it's going to be A-list with. Two-way is going to be A-list with, AC is going to be A-list with B, C, D, A, B, E, and D, E. And then AE is going to be A-list with B, D, E, A, B, C, and C, D. And that's 1 degree freedom. There's your ANOVA. And you should be able to verify, you should get all this. You verify this. Now notice, this is all, the exercise I gave you last time. You should be able to take a fraction, and once you know what the defining contrasts are, you can count for these, 1, 2, 3, then all those other effects will show up. How many total effects should I have? If it's 2 to the 5th, I should have 31 terms that are going to show up here somewhere. There's 31 terms because it's 2 to the 5th minus 1. Or, yeah, 2 to the 5th minus 1 is 31. And every one of those terms are going to show up. So you know where they are. Okay? So you're not losing information. And a good scientist is going to say, look, I know that never worked. That's never there. That's never there. You need to know your external material well enough to be able to make these judgment calls. But that's kind of conflicting the way people use these, especially in biology. You're using this kind of screen your information you don't know very much about. So there's always this give and take on these kind of designs. Okay, what resolution is this design? It's resolution. We have to look at defining contrast. Remember what resolution means? So,
4.
resolution is 3. Why? What's the definition of resolution?
It's the number of terms in your
Small is defining contrast. Yeah, resolution is 3. What does that mean? That means some aims is going to be A-list with 2 ways, and here you can see it. And this is a resolution. Here they are. Some mains are A-list with 2 ways. This is a resolution 3 design. It's resolution 3. Design. Some mains A-list with 2 ways. The question about this. It's a little different way. I thought, well, could you use this idea to use confound factorials? Can you use this idea to confound factorials? It's a little more difficult because you got to get the complements. You got to get all the other ones, so it's a little harder. But you maybe could use that idea. I'm sure you can, but I'm not sure it's any easier. Okay, so we're moving into there things I'm calling screening designs. So fractions, I first started saying, oh, fractions are screening designs. Well, the idea is we don't want to spend a lot of money on experimental material, but we have a lot of factors we want to look at. And so, well, half fraction is not too bad, you know. You only have half as many experimental units as you have total number of treatment combinations, but you can get some pretty good information. But why do you take this to the limit? Okay? And that's what I mean by screening designs, is that I want to screen, let's see, George has got 50,000 SNPs, right? I want to screen 50,000 SNPs with about a couple hundred lines. Okay? That's a screening design. And we can use these. In fact, we got a supersaturated design in the field with George. George is the plant breeding for the soy breeding program here. Okay? And it seemed to be quite effective. Where the columns are the SNPs. A SNP is a single nucleotide polymorphism, you see. And so you can think of the columns of these designs. This CRISPR-Cas thing that people have, now we can actually go in and actually set these things up the way we want them. You know? So I would really like to use a supersaturated design with CRISPR-Cas. I think that'd be really cool. We get that inside for you. Somebody knows how to do this stuff. You know? Anybody know how to do this? Mm-hmm. You know what it is? It's like you got scissors and go and cut out a piece of DNA and move around and put it where you want it. Okay, so we can really engineer these things. Okay, screening designs. So often we see in initial stages, often in the early stages, I've already said this, of a research program, we want to screen the maximum number of factors with the minimum amount of effort, or with the minimum number of experimental units. Minimum number of experimental units. Okay, so these are saturated designs. These things are, in fact, I should say this, these are called Resolution 3 saturated designs. These are saturated designs. That's kind of what these are heading toward. Okay? So why is a Resolution 3 saturated design? Well, it's the idea we're going to take it to the limit. So Resolution 3 saturated design. So the idea here, how far can I take this? I want to evaluate 2 to the n, 2 to the n minus m minus 1 factors with 2 to the n minus m experimental units. With these designs, you can take to the limit. With these designs, I can screen, and you can make these up yourself. They're easy to make. I can screen almost as many factors as I have experimental units. You know, if I have 16 factors, I can screen 16 factors with, or 50 factors with 16 experimental units. Okay? This is really kind of out there now, isn't it? Okay? So how would I do it? So if I want to screen the basic design, so if I want to say my basic design, this is my full factorial. if the basic design is 2 to the 4, right? So I get my full factorial to the 4th, right? And so I'm going to have 4 main effects, right, and all that. Just write down pluses and minuses. How many possible extra columns will I get? How do I get them? You see what I mean? I can have AB, AC, AD, BC, BD, BE. That's a 2-way. So you got to do all 3 ways, the 4-way, right? So how many total effects will there be here? 15. You see the idea? You know, I can have A, B, C, D. Okay, then I can have A, B, A, C, all the way out to the highest order, which is A, B, C, D, right? How many of these terms are there going to be with the mains and all the 2 ways? How many of them are there going to be? There's going to be 15. There's 15 of these terms. Okay, it's a 2 to the 4th full factorial. There's 2 to the 4th minus 1 effects. Okay, well we can, if we just let each of these facts be, so this will be factor E, this will be factor F, and so on, we can screen 15 factors. Okay. So that means I can screen 15 factors in how many runs, or how many experimental units? 16 experimental units. And you can write that design down yourself. Right? These are easy. I don't know who did this. George Box, who died a couple years ago, was doing these kinds of things. He's working for a big company. This had been right after the Second World War. He was doing something like this during the Second World War. But he worked for a big chemical company. It's still a big chemical company in Britain called ICI, and he was their statistician for this big, huge paint company. And he did a lot of these kinds of things. There's a big book on this published in about 1950, so I assume it was Box and Wilson and those people that really came up with these ideas. Anyway, it's all interesting in history. But they come directly out of science, just these problems we're talking about. This is not mathematics. This comes from you guys' problems. That's what to me is exciting about statistics, is it's a cultural thing. Okay, if I got a basic design of 2 to the 5th, how many factors can I screen? 31 factors in 32 experimental units. Okay, what if I have 2 to the 6th? I can screen 63 factors in 64 experimental units, and so on. And you can just write these down yourself. These are not hard. What's the hard part here? Running. Doing the work. That's what's so nice. You're sitting at a desk, you people go out and do all that unbelievable hard work. I just sit and see all the data, just put it on the board and stuff. Poor grad students. Well, your advisors have been out there too. It's embarrassing sometimes. If you're a stat student, you got to have respect for people's data in terms of the amount of effort they spend to get it. But you can see these designs, they're easy to understand and they're easy to use. And these people should be doing these kinds of things to screen the material, figure out where to spend their resources. And so, okay, they find some factors. They do a screening design, they find some factors that are important, and now you do regular replicating design of those. Okay.
So why do you have one more EU than you have vectors?
Well, I mean, notice you got, this is 2 to the 4 minus 1, right? So if you look at, you see the idea here? I got 4 main effects. I got 6 2-ways. Was it 10 3-ways? 6? No. Well, anyway, you see what I mean. There's 15 of those.
Right.
And so each one of those, I just give you another factor. So there's 15. There they are.
Okay.
You see the idea?
But what about the U's? Why do you have one more?
Well, I mean, when you write out your pluses and minuses, how many pluses, sets of pluses and minuses am I going to have? How many rows? And this one's 16.
Oh.
Right, you just start with that sequence of pluses and minuses. You have 16 rows. There they are. 16 experimental units. And each unit has that special combination of treatments assigned to it. 4 units. Okay, so these are resolution 3 fully saturated designs. Now, one of the problems with these designs, and this with the resolution 3 saturated design, is that look, they all have to be powers of 2. Is that the number of experimental units must be a power of 2. Here's the number of experimental units. Lou just said, oh, where the number of experimental units comes? Well, this comes from this, right? That's how many we have, right? All those have to be a power of 2. Okay, so the total number of experimental units is 16, right? These are all power of 2 over here. So that's where it's kind of limited. You say, well, what if I have 12 experimental units? Well, I should be able to screen 11 factors, right? Okay, what if you have 12 experimental units and you want to screen 11 factors? What to do? Well, this is a problem that was solved by some mathematicians. A guy named Plackett, another one named Burnham. And they probably knew Box, I don't know, but they were working on this. I'm not sure exactly where they were from, maybe Cambridge. But they're algebraicists, and they worked on this, and they used Galois fields to just get this new design. These are called Plackett-Burnham designs. Use Plackett-Burnham designs. And I'm not going to, in the advanced class, the advanced design class, we actually derive Plackett-Burnham designs using Galois fields. It's pretty nice. You need to know about algebra a little bit. And that's nice. Okay, well, Plackett-Burnham designs is you can screen if n is a multiple of 4 using a Plackett-Burnham design. Let's call them PBD. Using a PBD, you can screen n factors in n-1 runs. Can screen n factors in n-1 or with n-1 experimental units. Okay. Now, once you write that down, I've got a handout I want to give you because I'm not going to derive these. And once you see how to use these Galois fields, it's really not that hard. And all this is just going to be a sequence of pluses and minuses. Okay, so the top one. The top one is a Plackett-Burnham design. It has 12 runs. The runs are the rows, okay, and it has 11 columns. Those are the factors. Okay, so this is a recipe for with a 2-level design. Each factor is at 2 levels. In this case, to screen 11 factors with 12 runs. Okay. And so. It takes a while for this to adjust. I don't know. There. That doesn't help, though, does it? Well, anyway, you can kind of get the idea. Now, so here are the columns, which would be the factors, and then the rows or the experimental. I'm not sure what I'm doing wrong. That really didn't help, did it? Apparently people don't use this very often. Okay. Now, how do you get, say this is, so you can just take this table for one with 12 runs and 11 factors. But how do you want to get one, say for example, with, we got one down here with 19 factors and 20 runs. Okay? And so you can see this sequence of pluses and minuses. Well, let's look at the one with 12. If you look at the one with 12 in this table, 4.17, you look at this one with 12, and it has a row, it says that k equals 11, n equals 12. It has a row of plus, plus, minus, plus, 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 minus, minus, and so on. That's exactly the same as the first column up here. See the first column? I wish I could do something. I don't know. Maybe it's this. Oh, that's a little better. Well, anyway, you can see I can get, so I can take this row, and it's the first column without the last row. The last row, look what the last row is, it's all pluses. Or it's all minuses. They're all minuses, right. Okay. So now to use some of these other designs, you can just, these are generators. Okay. Now, generators, you'll remember how to use generators, although we used them a little bit differently. There's an interesting relationship between these Black and Bourbon designs and cyclic designs. So let's see if we can get the idea for the one with 20. So the one we have k equals 20, or k equals 19, and n is equal to 20. I'd put a column of these, and I'd say, if I can read it, plus, plus, minus, minus, plus, 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 minus, plus, minus, plus, minus, 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 plus, plus, minus, then put another minus, right? You have to put another minus on these. And now what do? Okay, that'd be for factor A, column A, unrandomized. I cycle them down this way, so I go to B. So I cycle them down like this. I go to A plus, plus, so I just cycle them down to the minus. See a minus there, then a minus there, then a plus, 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 minus, plus, minus, plus, minus, 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 plus, plus. Okay, then I have to go to the top, because I got to leave a minus at the very bottom, right? Then I go to the top, which would be a minus, and then I put a minus at the bottom. Okay, does everybody see this? It's same. So I can just, and this is C. And so I can, how many do I have? I've got 20 of these. What is the 20th letter of the alphabet? I don't know. Number 20. Whatever it is. Everybody see how to do this? They're easy to do. Okay. And there's tables of these generators you can simply construct. Now there's a complicated one here for n, or k equals 27 and n equals 28. And basically what you do with this one, this is n equals, or k equals 30, no, k equals 27, and n is equal to 28. What you do is let those three boxes underneath that be x, y, and z, and then you use a Latin square on this. So let x be, let's see, you can see it. Here's x, there's y, and there's z. Okay? And then you use Latin square, cycle on these. The Latin square is a cyclic design too. So you say x, y, and then z, and then y, z, and x. And now your whole design is this. Okay? Which would be, I think you have to add, then you have to add pluses on the bottom, right? No, maybe don't do on this one. But you see the idea how to do this. Some of these are fairly easy to do. Okay, so sorry about that. I don't know what I did wrong. I did something. Anyway. Okay, so that's enough for platinum design. How do we analyze this? How do we analyze platinum design? Well, this is a class about design, not analysis, right? So the analysis, I want it to be easy. What's the easy analysis you do for this? Just use least squares, right? You don't even need to do that. Look what you can do. You can just take, if you take your data points, okay, on the left here, take your data points, and the ones that have a plus, take the average of the ones with plus, and the average of the ones with minus, and take the difference, and that difference will be down at the bottom of the column. If that difference is large, that means that factor has an effect. Okay? Well, we can use least squares to do the same thing, but in the most general form, that's what you do is use least squares. Okay. So there's a number of ways to analyze these things. Simplest way, really, is to just get means of differences for each of them. So what I mean by that is if I would take, so for factor A, I'd take all these ones with pluses, take all those, and then get the mean of those. Okay, so I get the means of factor A that have plus, and then I take the minus the means of all factor A that have minuses. This is A. Add the minuses and get the difference. That's the difference you'd have down here. You put it at the bottom of the column. If that difference is large, then you know that factor is important. Easy analysis. That's what I like. Well thought out experiments, good designs, real easy analysis. Maybe you just use graphs to figure out what's going on, right? And these things are kind of amenable to that. Or you can use least squares. So analysis of fractions, resolution 3 designs, Plackett-Berman designs, etc. One way is just use these differences of means for every column. Okay? Compute differences of means. Means pluses versus the minuses. Right? Everybody see what I mean? Here's the mean. See what I mean? Make it solve. Okay. Another way, we can just use least squares. Well, fine, we can estimate these things. But the ultimate question is what? Wow, we're used to testing significance, right? So how can you test? You got problems with testing significance of these. Do we have any degrees of freedom for error on generally on these fractions or resolution 3 Plackett-Berman? We don't have any tests for significance. It's internally valid because we don't have experimental error from the experiment. Okay, so one of the problems is how to test significance. We talked about, well, one way is to use an error variance from the previous experiment. Okay? Well, that's one way. So we could, to test for significance, could, one, use error variance from a previous experiment. Experiment. Or, which I think is kind of a fun one to do, is to use QQ plots. And QQ plots are a visual way of assessing the effects of your factors. And so there's a procedure we have to go through here. If I can find it now. So QQ plots. We already talked about the one using the variances. So how to use QQ plots? But first, in fact, maybe you've already talked about this on assessing normality from your residuals in, say, 802. I think at least I used to talk about it. Okay, so let's use QQ plots. How do we do this? Well, the first thing we do with these kinds of designs is we fit a first-order model. Fit a first-order model. And then first order model is something like y is equal to b0 plus b1x1 plus b2x2. And so you have to use least squares on this. Up to b, say, bn plus e. That's a first order model. We can use least squares on this, right? This is b1, this is bn. So we get these effects. Here are my effects. I got actually n plus one of them. There they are, 0, b1, b2, and so on. And then the second thing is we rank the terms, rank the effects. So these are the effects here. And b1, they're just basically the slopes. Let's rank these where r sub I is the rank of the ith largest. The rank of the ith largest effects. When we approximate, then we got to approximate a probability. If we're going to make significance tests, we have to have probability. So whatever we do, we're going to have to relate to probabilities. So we're going to approximate the probability that a random variable takes on a value less than the ranked effect, and we're going to approximate that with take the r value or the ranked value divided by n. Okay. Okay, and let's see. So there are some other approximations. SAS uses a different. They both use different approximations. They use a different approximations here, but they're about the same thing. It's basically you take the rank number divided by the total number of effects, and I'm assuming the number of effects here is n. So I suppose to be formed like that to say this is n minus 1 here from the column n. Okay? Because you got the intercept in there too. If you rank the intercept, actually it doesn't make sense to rank the intercept, really, does it? So I think I have it right there. Just leave that out because you don't rank the intercepts. That's right. Okay. So now we get these ranks. Now we got to get the z values. Assume the data are normal. Now that's a big assumption here. We assume the data are normal, then we get the z value just from the standard normal table. Okay. Okay, so get a D, get the z values from a normal 0, 1 table. Now, how do we do that? Well, the idea is we get our r sub I over n, and that's going to be the value we're going to have right here. That's our probability value. Okay, so this is my probability x is less than bi is equal to that. And that's this point here. Now I think like a standard normal thing looks like this, right? And so I go back and hit the standard normal curve and I drop down and I get the z sub I value. So this is a cumulative distribution function of a standard normal. So I get these z sub I values. Now I'm going to have a z sub I value for every one of these probability values I calculate. Okay? And once I have those, then I can plot them. Okay, so I'll plot the z sub I on the y-axis versus the b sub I on the horizontal, on the x-axis. And so you'll get something that might look like this. So for example, how many people have seen QQ plot? Anybody? A few of you, okay. So if I get something that looks like this, so here's my z sub i's, and here's my b sub i's, and I get something that kind of looks like this, what does that tell you? Remember? It's normal. Yeah. So if they follow a straight line, your data are kind of normal, right? They're coming from a single normal population. That's saying all these effects are kind of coming from a single normal population. None of them are very important. Actually, what that says is none of the factors have any effect on the response. Okay, so none of the facts, no factors have effects. No factor has an effect. Well, what happens if I get one that looks like this? Most of them are like this. And all of a sudden I get a couple that are way out like this. So those are kind of like that. And then I get some that are just like this. These are kind of what we call outliers, I guess, right? Because they don't, these all kind of fall in a nice line, and those are all like they're all kind of coming from a normal distribution, right? But you got these two wackos out here. What are those wackos? You identify which of these effects over here. That's telling you which factors have a response. Okay, these factors have a response, are important. Right? And so that's how we use QQ plots. We can take any of these things we talked about. We can take fractions, Plackett-Berman designs, resolution 3, fully saturated designs, and so on. And we can always do a QQ plot and then look at these and see where the effects are. The questions on this? One other things that's kind of interesting about these is, look, we can, if you think of a variance in a normal, so if I go to 0, say a 0 is about up here, right? Okay, about. So if I go 1 unit below, say I go to a -1 here, and I go to 1 up here, that's how much on the standard normal. That's the standard deviation. Standard deviation is 1 under standard normal. I can go back and hit these things and drop down like this, and now I got an estimate of the standard deviation of the effect. Okay, so Lent says, oh, this guy's a retired statistician from Iowa says, oh, well, look, we can use these standard deviations now in some sort of a test. So not only can we estimate the effects using QQ plots, we can also estimate the standard deviations. Okay. Now I'm going to be wrong saying Russell Lent did this, because the first person, this guy named William Daniels, was a statistician, who's a corporate industry statistician. I can't remember who he worked for, somebody in Georgia. Very interesting. You can also estimate the standard deviation. So I got a handout on this also. So questions? I don't think I'm even going to turn on this thing. I don't think it's going to work. So sorry. I'll find out if I can get it to be there. But here's an example of QQ plots. Applied to data out of Montgomery. Montgomery is an industrial statistician in Arizona State for years. Actually, he's an industrial engineer. And he's in a nice book on experimental design. And the data comes from that. You know, I've done this many times with my own data, other European data, but I should take some of those out and use that. But I didn't. I just used Montgomery's text. And so they had, this is a plastic manufacturing experiment, and they had 5 factors, six factors: temperature, screw speed, hold time, cycle time, gauge size, and holding pressure. So maybe some sort of extruder or something, that's screw in it. But they're making some sort of plastic somehow. Okay, and then the response is the shrinkage. So they used a quarter fraction of a 2 to the 5th. So how many runs would be in a quarter fraction? Or 2 to 6. 2 to 6 is 64, so a quarter of that is 16 runs. So there's 16 runs, and you can see down below there's the data points. And then I have the ones and minus ones, and the high and low values for each of the different factors. Right? And now I had to recode. I actually had to put, if I'm going to use, I'm using PROC-REG to do this in SAS, I had to code the interactions. And so that's what the AB is equal to A by B and so on. I had to actually code the effects to use PROC-REG to do what I wanted. Although we can do it with ODS statement now really quite easily. Silently done it with ODS. So what you do is you do a regression on this. So step 1, you do regression. Here it is. With the polynomial, and that's what the PROC-REG is doing. So here's the model from PROC-REG. Okay, then I output this into a data set called B. So PROC-REG is doing this. He's outputting these things into a data set called B, and then I have to rearrange this data set called B that has my 16 effects. Okay, so I rearrange those into a data set, and then I have to rank them, and I can calculate these things. And that's what I'm doing here. I'm going to calculate these. Now, let's see. R star is R minus 0.5 over 15. This is, oh, it is 15. So it is 15 effects. Okay, so it is right here. I've got 15. Okay, but you don't calculate the intercept. Okay. And so I can calculate this thing. Notice how it's calculated. It's called R star down there at the very bottom. Okay. So it's a little bit different. It's trying to be consistent with the way SAS does it. And then I got a function called probit that does this thing here. Okay, this is a probit value. If you go backwards, that's the probit. And then I just plot it. Okay. And so if you go to the back of the next page, you can see what the QT plot looks like. Okay. So looking at this, it's almost similar to what I've had here. You got a bunch of them, they all kind of fall in a straight line, and then you have a few that are really quite far off. Okay, so B really had the biggest effect. And what is B? Screw speed, right? It's probably some sort of extruder, and they got thing that's cutting it up and moving around, and it's going really fast. So that has had a major effect. A is what? The temperature. So temperature and screw speed had the biggest effects. So in the example, the one out here was B, which was screw speed, and then temperature was down here, and then their interaction. And that kind of makes sense. There's really only two effects that are having response on this thing at all. Notice this is an unreplicated experiment. Okay, we can screen, what is it, 15 factors in 16 runs? Well, no, yeah, 16. 15, we can screen 15 effects in 16 runs. Okay? It's a resolution 3 saturated design is what this is. We don't have any replication. Okay? So usually in your earlier statistics classes, you can't do experiments without replication. Not true. You're a PhD level scientist. This is doctor of philosophy. The more you learn, the more complicated it gets. But you see, we can do unreplicated experiments as long as you know what you're doing and you put everything on the table. Okay, so one other thing I'd like to say, just passing the word about, is supersaturated designs. And supersaturated design, maybe I'll just say it. I've got a handout that you can get on the blackboard, and I'm not going to discuss it. The supersaturated designs are where you have more factors than you have experimental units. So if they're all two-level factors, and you have more factors than you have experimental units. Those are called supersaturated designs. That's in chapter 21 of the text in Giesbrecht and Gophers. And they're interesting designs, but those designs, you have to be careful because the assumption is most of the effects don't really have much, are not important at all. The assumption is most of them don't have any effect. There's only a couple of them that have a big effect. Okay. And so, well, I'm not going to be responsible for that, but that's just for your own knowledge. It is possible to push this even further. Okay. And so I really like that. I spend a lot of time doing supersaturated design. I've had students write written PhDs in that stuff, so that's fun stuff. Okay. So that's kind of enough about fractions. Oh, here, the R program's on the back, so if you wanted to use R, that handout I just gave you, the R program. All right, so let's summarize a little bit about fractions here. So what's the big advantage of these? And I stated it kind of at the first of the class. What's the major advantage? Why would you ever want to use one? Why would you ever want to use a fraction? They're unreplicated designs. You say, no, you can't ever get information from an unreplicated design. Well, I beg to differ. So one of the advantages of fractions.
Save money and time.
Save money. Number one thing, always worry about money. Right? Actually, for you grad students, it's money. You'll get money later. But it's your sleep you worry about, right? So, fractions, save money and time. Advantages. Save money, save experimental units, I'll say that. Money and time. Save experimental units, money and time. Okay? And we can look at, we can evaluate many effects, right? Many effects or factors. What's the disadvantage of these things? There's no free lunch, right? So you tell your advisors who've never heard this, look, I got a new design where we don't have to replicate, we only have to have one more experimental unit, we have factors, okay? And your advisor gets all excited about it. Then what do you say? Well, wait, what's the problem with these, right? What's the problem? What's the disadvantage? What's the first one? First major disadvantage. Well, maybe I shouldn't order them, but somebody tell me one.
Many component.
Yeah, you totally lose information on the one of several facts, right? So you lose all information on some effects. What do we call these effects? Defining contrasts, right? We use all of the information on defining contrasts. What about the other effects?
Using higher order effects or higher order interactions on.
Yeah, well, they're A-list, they're confounded. Every effect is A-list with a bunch of other effects, right? Okay. All other effects are confounded with other effects, or A-list, with other effects. What about test of significance? There are some kind of formal tests of significance, but there really aren't any really strong methods of statistical inference. Okay, so there's only weak methods, only say ad hoc methods for statistical inference.
Hard time to publish.
Well, if you do this, I mean, it behooves you to. In fact, there was a PC committee the other day, and there's a bunch of stuff in there that was not well described. So I went into the references and tried to see what's going on. The references didn't describe any of it. So if you're going to use a fraction, you can't just say, I'm using a half fraction of a 2 to the 4th. You're going to have to go and say what it is, and then at least give some citations that say what it is to be able to justify yourself. And so you're going to have to educate your readers a little bit on this. If you're going to get them to accept it. If they're not going to accept it, they don't understand it. Well, maybe they will. Maybe they're more likely to accept it. But it's a good point. It's hard to get these published. So, questions about fractions? Anything about fractions?
Can you? So I feel like I lost your explanation when you did this last graph there with the.
Or signal?
Yeah.
Well, I mean, if this is a z, right, a z has a normal, right, with a 0, and that's 1, and that's minus 1, right? 67% between it. These are my z-sub values, right? And what is that? That's a standard deviation from a normal. So standard deviation is equal to 1. Yeah? Well, so I'm taking, okay, that's from a standard normal, there's my standard deviation, 1 from a standard normal. Now I just plot that back and go, and now that distance right there is going to be the difference of the standard deviation from the back. Okay. There's a 1-to-1 relationship, so you can just say that.
So on your y-axis here, you have the z or zi.
These are the zi's, right?
Okay.
Right. Other questions? Okay. Now I'd like to start talking about response rates again. And they kind of come out of this. And they're not too hard. I mean, given the things that we talk about, response services, I think, are kind of fun, at least at this point. I mean, I think at this class, for a lot of you, they've kind of done some heavy lifting up to this point. And response services are a little easier in some sense, but maybe conceptually and analysis and that kind of thing. Maybe it's not as new. A response service methodology. Broad surface methods. And there's a number of examples in biology and industry where you want to do these kinds of things. The idea is that we're going to assume all factors are quantitative. This is the first thing. You can't do it unless, you can't use standard response surface methods unless all your factors are quantitative. And the main goal with these things, generally, not always, but the main goal is to determine the levels of each factor that will optimize some response. Of the factors that will optimize, and I'm using the word optimize to mean maximize or minimize, as max or min, some response. So an idea might be so you were optimized. Yeah. Pardon, what were you optimized? I can't remember.
So I was using them for extrusion, and I had 3 variables: temperature, screw speed, and moisture content.
Yeah, that's right.
And I was trying to optimize their levels to get maximum expansion.
Okay, you got to do product. It's like you're making, these are wheat puffs or corn. It's a food product from an extruder. Okay, so example, what levels, let's see, moisture content, right? What levels of moisture, screw speed, and temperature maximize the expansion of a product that you're producing, okay? That maximize, what is the levels that maximize the expansion of an extruded product? First question, can she do response surfaces? Well, yeah, she did, but why can she do response surfaces with this? Because moisture is quantitative. Okay, you can adjust moisture, right? Because screw speed, that's how fast you can just turn up the speed on these things, and get it to go faster or slower. So that's quantitative. Temperature is quantitative too. Okay. One of the problems with these designs, at least with use a response surface with an extruder, is usually the temperature is applied to the whole machine, and the screw speed is easy to change. The moisture temperature is hard to change, and so that gives rise to split plot and whole plot, split plot type problems. Okay, which I think is kind of what we were talking about. Did else have another example where you're using response surfaces? Anybody? Well, you might think in plant sciences, because you do a lot of plant scientists in here. What's the obvious one in plant science? Yield is your response, right? Going one response, yield. So plant science. Another example, you want to find levels of N, P, and K that maximize yield of a certain plant. That actually is a response to this problem. The problem with these is these surfaces, they're not nice and curved like this. They'll go up and they'll flatten out like that. Of course, you kill your plants and put too much of this stuff on it. So they'll go up, they'll be flat for a real long time, and then they'll crash like that, you see. And so, you get into all kinds of problems with the type of surfaces that they fit. But still, scientists, this is what they spend their life doing, actually. These are the response surfaces. Anybody else have another one? Well, okay, you see the idea. There's another idea. So overall objectives. This is my goal. In terms of making decisions, the way you can kind of structure it is I got a main goal, and I have several objectives used to achieve that goal. So the objective, yeah.
Can you only have 3 factors?
No, as many as you want. It's how much money you have, right? Always comes down to that, right? And so we're going to be using factorial with these. Same kind of idea as factorials, it's just all factors have to be quantitative. So objectives are response service methodology. Our goal is to optimize some process. Is first of all, we want to find the region of the optimum. Look, if you just try to do one great big experiment, I see people doing this all the time. Response service is sexy. I want to use that and get a paper out of it. And they want to do one great big experiment with response service methods and use this really nice design. The problem is, it's like, okay, I want to get to the top of Mount Everest, but I'm starting, way too far away. I'm starting in Nebraska, and I want to get to the top. Well, I mean, you have to get a surface. It's so irregular. You have to have a nice, smooth surface to get these things to work. So you have to get near the top first before you can really say it. So you have to have kind of hill climbing methods to get to the top. Okay? And I'll talk about that. This is kind of using the ideas of paths as steep as ascent. So once we're in the region, how to design experiments in the region of the optimum. How to design experiments to estimate the surface. And then finally, number 3 is estimating the surface, finding the optimum. So the last one is, how do we actually estimate the surface, find the optimum, and explore the optimum? So the third one is estimate the surface. And optimum, and explore the surface. That's not too hard with only 3 factors, but what if you have 6? That's 6-dimensional space. Okay, so we're going to have to use some algebra. Okay, so I'll stop with this and we'll continue with response service next time. So the last 2 questions in the homework, hopefully by Wednesday you should be able to do all of them. Certainly you can be able to do the third one by Monday. Okay, the exam, let's see, the high was 98. I was impressed. The low was 52. The median was 76. Most people did pretty well. Don't get discouraged if you didn't do so well. Just figure out what you did wrong. And see if you want. Javi. Mara. Ashley, she's not here. Vincent. There, girl. Let's see. Sean. Artie. Jamie. Right here. Wakma, right? Lachana. Sorry, Lachana. Here. Jessica. That's it. Anybody have one? Okay. Well, most people are getting it, but if you didn't do as well as you want to, then don't get discouraged. If you want to come by and see me, no problem. We can check. So I'll see you next time.